Welcome to my presentation. I'm Bingheng Wang. I'm very glad to introduce our work, Differentiable Moving Horizon Estimation for Robust Flight Control. I will first give the background of disturbance estimation using moving horizon estimation. Then I will point out the challenge of tuning DMHE and present our auto-tuning estimation algorithm that can be trained efficiently. In many flight scenarios, complex disturbances will be generated when the quadrotors interact with the environment. For example, during takeoff and landing, the ground effect will increase the lift force. When pushing movable structures, a quadrotor will be subject to an unknown reaction force that prevents it from moving forward. These disturbances affect the quadrotor behaviors significantly, but in general, cannot be measured directly by quadrotors. So we need a robust flight control strategy to estimate and counteract the disturbances. Our estimation goal is to estimate three-dimensional disturbance forces and torques using moving horizon estimation because of its superior performance in robustness, convergence, and accuracy. With the most recent measurements in estimation window, previous estimates, and control inputs, an MHE can find an estimate of disturbances by solving this nonlinear optimization problem that best fits these measurements, where we extend the quadrotor states with disturbance and likewise augment the quadrotor nonlinear model with a random walk disturbance model. At the next sampling, we move the estimation window forward and repeat this optimization again. The MHE solution, in fact, is very sensitive to these weight matrices, which are related to noise covariance. For example, for a group of non-optimal parameters theta, we have a corresponding estimate trajectory. We can evaluate the estimation using a scalar value differentiable loss function. We formulate the loss function based on the quadrotor tracking errors rather than disturbance estimation error because, in practice, the ground truth data of disturbance is difficult to obtain, such as aerodynamics and modal uncertainty. After tuning the parameters to be optimal, we may obtain a best solution with the optimal loss value. However, tuning these parameters is non-trivial because noise covariances are usually unknown in practice and hard to identify. So tuning MHE is very sophisticated and needs much expert knowledge. To reduce the burden of manual tuning, we propose to tune MHE automatically by gradient descent. For tuning MHE by gradient descent, we first need to solve the MHE problem to obtain the estimate trajectory with the given parameter. Then, we optimize the parameter by minimizing the tracking error-based loss function subject to the MHE estimate trajectory. So this hierarchical architecture shows that tuning MHE by gradient descent is a bilevel optimization problem. In the higher level optimization, we need to calculate the gradient of the higher level loss function with respect to the theta in backward propagation. In this chain rule, since the higher level cost is an explicit function of the MHE solution, it should be straightforward to calculate the first term. However, the key is how to efficiently calculate the second term. The MHE solution must satisfy the KKT conditions of the nonlinear MHE problem. The nonlinear model makes it difficult to solve the KKT conditions directly. So calculating the second term is very challenging. We address this challenge by implicitly differentiating the KKT conditions of the lower level MHE problem. This implies that the MHE solution is differentiable with respect to theta, and this is why the proposed algorithm is called differentiable moving horizon estimation. By defining new variables and matrices, the differential KKT conditions can be obtained. The differential KKT conditions share a similar structure to original KKT conditions of the nonlinear MHE problem. So it can be viewed as a new set of KKT conditions corresponding to an auxiliary MHE system whose solution is exactly the gradient. The auxiliary MHE system has two important features. Its dynamics model is linear and the cost function is quadratic. This means that we can obtain the analytical gradient by solving this auxiliary MHE system. We propose to solve this auxiliary MHE system very efficiently by using a common filter. So interestingly, the analytical gradient can be solved in a recursive form, which makes the algorithm computationally efficient. To validate this property, we measure the running time of the algorithm for a quadrotor model. As we can see from this table, even when the horizon increases to 50, the computation time is only 13.1 milliseconds. This means that the algorithm is lightweight enough for real-time execution on a quadrotor. With the analytical gradient, we developed the model-based policy gradient algorithm to train the DMHE directly from the tracking errors. In the forward path, given the parameter theta, we solve the MHE problem to obtain the estimate trajectory. Then we can compute the higher level loss function based on the trajectory tracking errors. Next, we solve the robust control law that takes the estimated state as a feedback and uses the estimated disturbance as a feed-forward term for compensation. After that, we implement the controller to get a new state. In the backward propagation path, we solve the auxiliary MHE system to obtain the analytical gradient of the MHE solution with respect to the parameters. Then we apply the chain rule to obtain the gradient of the higher level loss function. Finally, we use gradient descent to update the parameters. We evaluate the model-based policy gradient algorithm in extensive simulations. We train the DMHE by making a quadrotor take off and follow a figure-8 trajectory under various disturbances. The disturbance estimation figure shows that untrained DMHE responds slowly to time-varying disturbance with large estimation biases and delays. So untrained trajectory in this 3D plot shows large tracking errors. After training, both the tracking and estimation performance are improved. So this result validates that a stable MHE with fast dynamic response can be learned directly from the trajectory tracking errors. The improvement of performance is due to the auto-tuning algorithm that optimizes the weight matrices. In the simulation, we set the process noise variance to be much larger than that of measurement noise. We also introduced the forgetting factors gamma 1 and gamma 2 to account for the historical data in one horizon. In this case, we should have set a large RK as we had high confidence in the measurement. To highlight the efficiency of our proposed auto-tuning algorithm, we set the forgetting factor gamma 1 much smaller than gamma 2. So without training, the performance of untrained DMHE with the initial weight matrices is very bad. After training using the proposed algorithm, the trained DMHE can respond quickly to the aggressive disturbance. By comparison, all elements in measurement weight matrix are larger than those in process noise weight matrix, and gamma 2 is stable around 0.2, while gamma 1 increases to around 0.95. The optimal forgetting factors further make RK much larger than QK. So the weight matrices were optimized to agree with the settings of the noise variance. Another advantage of our proposed DMHE is that its training is very efficient. In this figure 8 tracking scenario, only 3 episodes are sufficient to make the tuning parameter reach their local optima. So our DMHE is more efficient than those neural network-based estimation algorithms in terms of training time and computational complexity. This is a benefit of model-based methods. Now it's time to summarize our work. we propose a differentiable moving horizon estimation algorithm. DMHE can tune its weight matrices automatically by gradient descent for accurate estimation. We calculate the analytical gradient by using a common filter in a recursive form, which enables efficient learning. Our estimation shows that a stable MHE with fast dynamic response can be learned directly from the trajectory tracking errors. In the future, the DMHE can be embedded as a layer into large deep neural networks for joint training. We believe that the proposed auto-tuning MHE can help improve quadrotors robustness and adaptation to various challenging scenarios. Thank you for your attention.